Hello? There we go. I think the audio is better now. Oh, it's actually worse because I can hear myself. This is very bad. Okay, who do I need to mute? All right, I think I found the right mute button. Hello, everybody. Happy Friday. Um, let's see. And we have people here. Let's make sure people are actually here. Seems like it. So one time I did an entire live stream and I messed up. Oh, hello, great. One time I did an entire live stream and I messed it up. Like I thought I was streaming, but I was not, and it turned out I was actually talking to myself for an hour. And I just don't want to repeat that. I felt very very dumb at the end. I guess it was really embarrassing, but nobody was there to see my embarrassment, so that's like a silver silver lining, I suppose. All right, let's get into this. I'm gonna do some keynote now, and then yeah, let's do this. All right, I think too many windows here. So OBS, there's OBS. Okay, great. So, welcome to the live stream, everybody. Today we're going to be hacking on, wasted embarrassment. Yes, exactly. Thank you, Sean. We're going to be hacking on YJIT today with Maxime. So yeah, let's do that. I'm going to do, as usual, I'm going to do a short presentation about YJIT and different stuff. I'll bring on Maxime. We'll talk about things, and then we'll actually hack on YJIT today. Okay, where the heck is my keynote screen? There we go. Okay, yes. Happy Friday, everybody. As usual, happy Friday. Last time we hacked on Vernier. I think it was about a month ago. We were doing profiling then. Today we're gonna be doing some hacking on YJIT. Last time I did a live stream, somebody requested that we do some YJIT work in Rust, and that's what we're gonna do today. So I take requests. If there's anything you want to see inside of Ruby or any implementation details that you're interested in, let me know, and I'm happy to do a live stream about it. And as usual, if you have any questions, put them in the chat, and I will try to answer your questions as best as I can. Today we're actually going to talk about kind of getting started on YJIT. So getting started hacking on it, what the internals are like, how it works. So we'll start by talking about what is YJIT or what is a JIT. We're going to talk about how YJIT works. Then we're going to do kind of an intro into how to hack on YJIT, like the code layout, where to find things, and how all the bits glue together. And then we'll talk about today's optimization. We're going to actually implement an optimization today, so that you can see what it's like to actually hack on YJIT internals. I'll chat with Maxime, and then finally we'll do the hacking together. So first off, what is a JIT exactly? And I think most people know what a JIT is exactly. It's just a thing that makes your code go fast, which is great. We like fast code, but when I'm hacking on a JIT compiler, I actually like to keep in mind just kind of the fundamentals of what a JIT is, because I think it helps me think about how to solve the problems in the JIT compiler. And all a JIT is something that just generates machine code at runtime. So we're taking our Ruby code and generating machine code from that Ruby code. So we take our Ruby code, and then all we do is at runtime we do a conversion from Ruby code into machine code. That's all we're doing. Of course, there's a lot of algorithms and stuff around that, but at the end of the day, we're just generating machine code at runtime. YJIT actually provides a really nice way so we can see the machine code that we generate. So if you have YJIT enabled in dev mode, so you have to configure with -- enable YJIT equals dev, and we'll look at this in the terminal. If you configure it with dev mode, you can print out the disassembly. So you can print out the machine code that YJIT generated. So if you run this code that's in the slide here, you'll get the machine code printed out here. So you can see, you can kind of see what the machine code is that we're generating. So How does YJIT work? Like, how does this thing work exactly? Well, the way it works is we have to take multiple passes on our code. So you and I, we just write Ruby code as text files, and the very first thing that happens is we take that Ruby code and we convert it into bytecode, YARV bytecode, and that bytecode is created by parse.y and compile.c. So if you look in Ruby's source code, these are the two like important files for converting our Ruby code into YARV bytecode. So the next thing that happens is the Ruby virtual machine, or YARV, will execute that bytecode. That's our normal procedure. And if we happen to execute that code enough, then what we'll do is we'll convert that code, that YARV bytecode, into machine code. And the thing that does that is YJIT. So YJIT is the bit of code that takes our YARV bytecode and converts it into machine code. And once we've converted it into machine code, we'll execute that machine code on the CPU rather than inside of the virtual machine. And once you've explained YJIT 30 times, it goes faster. Yes, that is correct. So hopefully we're executing the machine code on the CPU, and hopefully we're not entering back into the virtual machine again. We want to spend as much time in machine code as possible, but sometimes we have to go back into the virtual machine. So really, Ruby contains two compilers. One compiler is in compile.c, which is our Ruby to YARV compiler, and then the other compiler that goes from YARV to YJIT. Someone is asking, it goes from Ruby to bytecode, no C in between. It goes from Ruby to bytecode, yes. So some methods are implemented in C, but we take all of the Ruby code that you write in your Ruby text files, those get converted into bytecode and executed with the virtual machine. So compile.c converts our Ruby code into YARV bytecode. YJIT takes our YARV bytecode and converts that bytecode into machine code. And when you're hacking on YJIT, the point of this is when you're hacking on YJIT, you're mostly dealing with the bytecode that YARV generated. You're not dealing with the actual source that somebody wrote. So in order to hack on YJIT, you kind of need to know a little bit about the bytecode that YARV executes. And if we go look at if we go look at YJIT's internal, specifically codegen.rs, you'll see a really big map in it near the bottom of the file that maps YARV bytecode instructions to YJIT generation functions. So this is just the top. This screenshot is just like the top few bytecodes. So like you see, we have YARV instruction nop is mapped to a function in Rust called gennop, and then all these. That's all we're doing is just making this map between them. So the other thing to explain about YJIT is the algorithm it uses, which is called lazy basic block versioning. And this is a technique that was invented by Maxim for her PhD, and she's going to join us, and we're going to talk about it. But you can read her paper at the link below or in the QR code above. I'm gonna do my best to explain the algorithm, but fortunately she is here to correct my mistakes. But I'm going to explain a little bit about it, or how I understand it. So lazy basic block versioning is extremely lazy. And I just want to do a high-level overview of the algorithm so you understand what it is when you're hacking on the JIT compiler. So normally, like, if you have a method-based JIT compiler, what'll happen is after we've executed this method so many times, like let's say we executed a bunch of times, or whatever, some heuristic, let's just say number of times executed. If we execute that enough times, it'll take the entire method and it'll convert that entire method into machine code. Now, this is how a method-based JIT compiler will work, and this is different from how an LBBV compiler will work. The way an LBBV compiler works is, instead of compiling the entire method, it's just going to compile, like, once it gets to, time to compile, it's just going to compile, like, some of it. So basically, it compiles up until there's certain things, like, for example, a branch statement. So in this example, we have an if statement. So it'll compile all the code up until the if statement, and then it doesn't compile anymore. It stops right there, and it inserts two jumps at the end of the machine code, one for each side of that if statement. And what it does is it waits, it lets the machine code run, and whichever side of that if statement executes, that jump jumps back into the compiler. So it jumps back into YJIT. And we call these jumps here, we call them branch stubs. And these stubs will jump back into the compiler, and then the compiler will only compile that side of the branch. So for example, in this case, maybe user.displayname needs to be compiled. So it'll compile that, it'll generate the machine code for that, this thing. Did I do that right? Yes, it generates the machine code for this side of the branch, and then it rewrites the jump in our machine code. So the next time this is executed, instead of jumping into the compiler, it'll just jump to the newly generated machine code. So this way, we're like extremely lazy. We don't compile the whole method. We only compile like the stuff that we actually need to compile. So the advantages of this are, well, we compile as little as possible. So if there is some code, like you've written an if statement, if one side of that if statement's never executed, we just don't compile it because there's no need to, which is really, really, really nice. It's fast, of course. It means that we have really fast startup because we don't have to compile as much code. We have a very low compile time because we're not compiling as much stuff. And a really great advantage is that we're able to learn types. So we can learn runtime information based on the code that's actually executed. So for example, like let's go back to this method where we do display, show a greeting or whatever. When we pause here to compile, like we insert that jump statement. When we pause, we can actually check, hey, what type is user? What is this? What is this thing? And since we're able to learn what that type is, when we compile this interior where we have to compile, when we compile the interior, the if statement, like that user.displayname, we already know what the type is of the user variable, so we don't have to emit any extra checks. So it means that we can learn type information and propagate that type information through the code. So this is a really, really excellent and powerful feature of the algorithm. Okay, yes, did that. Great job. Great job. So let's talk about, we've kind of talked about how YJIT works. Let's talk about how to hack on YJIT. So when you're looking in the Ruby source code, I was really struggling with a way to show this on a slide, but there's so many files inside of Ruby core. Like I was gonna show okay, here are the files, but then it's just way too long. I can't read it. Max B is asking, do you eagerly insert type guards? We insert type guards when we do the very first type check. So when we learn the type, we say hey, we see this type here at compile time. We insert the type check at that time, but any code that's dependent on that doesn't need to insert the same type checks because we did it once. Okay. So all the .c files in the Ruby, the root of the Ruby source tree are the C Ruby implementation. There's one special file with regard to YJIT. It's YJIT.c, and this C file is it's the glue between YJIT and C Ruby. So it's kind of C routines that we need in the Rust implementation in order to deal with C Ruby internals. If you look at where go to the next slide, please. Thank you. And say go to the next slide, please. That's me. I have to change the slides. So inside of YJIT source star, all that stuff is the YJIT implementation. And there's two really important files in there. One is core.rs that contains, hello. There's core.rs, which contains all the YJIT data types. So when I said that we keep track of types, the type of the local, we have to keep track of that inside of a data structure, and we call that the context. There is a context object, and you can find that definition inside of core.rs, as well as other helper data structures like the information about the stack, registers that we use, things like that. Inside of the other important file is codegen.rs. That's where we take the YARV bytecode and we convert that bytecode into machine code. So when you want to convert something into machine code, this is the thing that you need to look at. Stuff under source backend, that's platform specific IR. This is kind of stuff you probably won't have to deal with when you're hacking on YJIT. It's just we have a small intermediate representation that we use because we want to generate code for x86 or ARM. Most of your time really will be spent in codegen.rs. So if you want to hack on YJIT at all, most of your time is going to be spent in this file. Ah, crap. I did mess up a slide. Okay. There was one more I need to fix. This slide is incorrect. It should be... Oh, let me just fix it. All right. I'm going to fix it. This is... this is a just-in-time presentation. Okay. Configure, it's got to be enable dash YJIT dev. Okay, let's play that again. There we go. All right. So when you build Ruby, run autogen sh, and then in order to configure YJIT in dev mode, you need to do -- enable -YJIT equals dev. YJIT's enabled by default, but it's not in dev mode by default. So you want to be in dev mode when you're hacking on it. So let's take a look at today's optimization. Today's optimization, we're going to be looking at array pack, and we're going to implement that in YJIT. And actually, in October, I did a live stream where I implemented the optimization in the Ruby VM. I'll put this link in the description if you want to go watch that. But we implemented it in the Ruby VM, but I don't think we implemented the YJIT side of things. Today, we're going to implement the YJIT side of things. Basically, what this optimization is like, let's look at how array.pack works normally. So on the left here, we have our Ruby code for packing 3 floats into a string. When we execute this, on the right here is our YARV bytecode, which I'll try to get out of the way for when we need to. So the bytecode is on the right. Our VM stack is kind of right there in the middle. When we execute this, first thing we do is we get local A. It pushes A on the stack. We get local B, pushes B on the stack. We get local C, pushes C on the stack. Then we create a new array. Come on. Thank you. We create a new array, and it pops those 3 values off of the stack. It creates a new array. And then we push the string FFF on the stack. Oh, there we go. And then we call a method, and that method pops the 2 values off the stack, and it puts the string onto the stack. So whatever that string is, I don't know what it is. It doesn't matter. It's just the string. So the optimization that we did is we said, well, we don't actually need that intermediate array because we just use it and then throw it away immediately. There's no reason to allocate that array. So what we can do is we can say, well, let's push these 3 values onto the stack. Boy, I should have practiced these slides more. Come on. Next slide. There we go. So we'll push the 3 values onto the stack, and then instead of allocating a new array, what we're going to do is we're going to push the string FFF onto the stack, and then we'll have this special instruction here, opt_pack3, opt_pack. And what that does is it says, hey, I need you to pack some values, but instead of creating an intermediate array, I want you to just take a look at these 3 values on the stack. So we're going to use the stack as the underlying array, and then it'll just create our pack string. So it'll pop all 4 values off and create our pack string. So we don't have to have that intermediate array that we just throw away. And we can see the changes in the YARV bytecode. On the top is the original bytecode. Top is the original bytecode, and the bottom is the bytecode after the optimization. Kind of hard to read. Don't worry. The difference is this. So you can see before we were creating a new array and sending a method, and after we just call this new array send thing. So our job today, after we chat with Maxime, is we are going to add new array send pack support to YJIT. And that is our job. So we're actually going to do some hacking on that. So now I will welcome Maxime on. Let's see. Hello, Maxime. How are you?
Hi, I'm good. How are you?
I'm doing well. Thank you. If anybody like everyone, if the levels are need to be changed, let me know. The audio levels need to be changed, let me know. But anyway, Maxime, it's great to have you on. Um, I have a question for you. I asked people like if they have any questions about YJIT, please tell me, and then I would ask you. And the first question I got was, um, so you're the creator of YJIT. Why, why no JIT? Why not JIT?
That is a good question. Legitimate.
I'm just kidding. Actually, I'm not kidding. That was really the first. That was really the first question that I got. Okay, Maxime. So you got your PhD in compilers. Is that correct? From
Uh,
University of Montreal.
yeah, I specialize in compiler design.
Nice, awesome. What got you interested in working on compilers?
I think I've been interested for a very long time. Like even when I was an undergraduate, um, I think I learned to program as a teenager, and I got very into like just enjoying programming. Enjoying like building little things because programming is kind of like you have an infinite set of Legos where like the only limit is your time and imagination.
Yeah.
So there's something very very fun about that. Um, but I think as I got more into programming, there's I kind of started to wonder, well, how would you go about creating your own programming language, and how does it work behind the scenes, right? Because it's like computers don't run programming code, right? They run machine code and
Mm-hmm.
machine instructions, and so like the compiler is the missing piece that goes in between like the source code and machine code, and it's kind of like how the sausage is made, so to speak.
Mm, interesting. Myra says they listened to the Ruby on Rails podcast session about YJIT and said it was really great. So,
Oh, thank you.
um, while you were studying, actually, I have I'm gonna make a joke, but then I have a serious question. So, so while you were doing like studying in college, did you write a lot of Unicode? Sorry. Okay. Okay. So serious question. It's really interesting to me that you would get in like you get into compilers because I think like a lot of programmers they want to build kind of an end product. You know what I mean? Like they want to build a website or they want to build like a thing that they would use. When you're working on compilers, it's like this is specifically a like enabling somebody else to do a thing. Like why did you get into that? Is it just curiosity or
Yeah, well, I think first of all, it's really good to have a project to motivate you to learn things, right? I think one of the best ways to learn is if you have some kind of an objective in mind, something that you want to create, and then you kind of work backwards, and you're like, what technologies could I use? What features do I want to have? What technologies could I use? What are the
mm-hmm.
restrictions I can work with? And yeah, so I think it's really good to be kind of like goal driven like that. Um, I guess I think about compilers also as kind of like a product
mm,
or a goal in itself. Um, and I guess for me personally, like I was very interested in yeah, and just the idea of like building new programming languages and exploring
mm,
new possibilities in that space. But there's also something that makes compilers fun in a sense is that compilers can have very few dependencies.
uh
So you
yeah,
can
that's
you can
true.
be
Yeah.
yeah, you can be pretty insulated from uh a lot of potential breakage, let's put it that way.
you, you don't need to install 1,000 npm packages just to build your compiler. Yes, I absolutely understand. I understand the appeal of that. Um, so you like you worked on your LBBV paper in school. How did you come up with this technique? Like what inspired you to do this? How did you think of this?
Right, so it's kind of like a couple of steps, so to speak. But like I did a master's at McGill, um, with my advisor then, Professor Laurie Hendren, um, and she wanted me to work on building a JIT compiler for MATLAB, and I think what she had in mind was that I would be doing optimizations around like numerical computation. So there's different optimizations you can do to do like operations on matrices more efficiently. But I guess like the thing that really stuck with me is that MATLAB is a dynamically typed language. And so like before you can do all these optimizations on matrices, you have to know that you're even working with a matrix to
Right.
begin with,
You
right?
need to know the type. Yeah.
Yeah, it's not a boolean,
Yeah.
you know. And then so I got into building like a whole like type inference system to like infer the shapes of matrices and vectors. And um and I, I I I started working on something that used like versioning. So this idea that like when you're calling a MATLAB function with some arguments, you can create like a specialized version of that function that knows the types of its arguments, and then you can propagate the types inside of the method, and you can use like the versioning of functions as like a device for propagating the type information. And then when I went on to do my PhD with my advisor Mark Philly, we decided to work on JavaScript. And what I really wanted to do was to build what's called a hybrid type analysis.
Okay.
So the idea of a hybrid type analysis is that when you're in a language like JavaScript, one of the problems that you face is that you can load new code dynamically. So people can eval new code, but also if you've done any web dev, like you know that you can kind of like load new JavaScript files on the fly, and so that makes it really hard to do type inference because like the compiler can only see one part of the program, and it's hard for the compiler to guarantee like no new code is going to be ever loaded from this point.
Mm-hmm.
And so you could run your type inference, and some new code could be loaded and it could come and like break your type inference results.
Right. Break all of your assumptions that you had. Yeah.
Yeah, in which case you have to de-optimize. So the idea of like the hybrid type analysis is kind of like you do as much of the type analysis as you can. You keep track of the assumptions that you're making, and then if some new code gets loaded, you invalidate that, and you kind of like restart your type analysis from where you were.
Mm-hmm.
But the problem I ran into is like I worked on this thing for about 2 years, and then some researchers at Mozilla published basically exactly what I wanted to do.
Oh.
Uh,
Okay.
but yeah, but they also did it better, I think, than mine would have been.
Oh. Oh. Okay.
And then I ended up having a conversation with my advisor, and it was kind of like at first, he was like, oh, I'm sure yours would be different, like it wouldn't be exactly the same. But then we kept, we read the paper and everything. I was like, no,
No, it's the
no,
same. Oh no.
it's the same but better. Um, so then I did like a little bit of soul searching for a couple of months,
Mm-hmm.
and we ended up kind of like brainstorming about different ideas, and one of the ideas that came up was that maybe we could like lazily we could do the type versioning at the level of basic blocks.
Mm-hmm.
um and using that we could get like more precise results and do it faster than like a traditional type analysis, and
Mm-hmm.
we could avoid like, because one of the issues with the hybrid type analysis is that you need this thing called unstack replacement,
Mm-hmm.
where when you de-optimize a method in a method based JIT, you might need to replace the optimized version by a de-optimized version, and it can be pretty expensive to do. Like it can be like a lot of complex machinery and pretty expensive to do. But with the basic block versioning approach, you don't really have that problem because you can kind of like play a special trick where you can always generate a new basic block version that's like compatible with the type information that you have coming in.
Mm-hmm.
So it's like you can generate code for like the continuation, and you can continue execution from anywhere.
Hmm.
So it kind of like gets rid of the all stack
On stack
replacement
replacement
problem.
problem. Yeah, that's
Yeah.
nice. Yes. Yes. That's
Um,
awesome.
and I guess the final piece was we ran some first experiments, but we faced the problem, which was that uh, when you do basic block versioning liberally, you can get like an explosion of basic blocks.
Yeah. Okay.
So, but then when you do it lazily, like you can basically completely solve that problem.
Right, because you're only generating the ones that you need, so it's by definition the minimum. Yeah, yeah. It's great. Awesome. I think we should start our coding adventure now. Let's
Sounds good. Let's
let's
dive
do it.
in.
Yeah, so we're gonna do. I think what I want to do is we're gonna start off by looking at the. We're gonna start off by looking at the YARV instructions file, specifically the send instructions, so that we can see um, how the Ruby virtual machine jumps into YJIT first, like how it enters the compiler. Then we'll go take a look at the compiler itself, and then I guess like fix our thing. So, all right, let's do it. Let me move my thing, move my keynote, bring up our desktop. Okay, there we are. We're on desktop. And right, if anyone has any questions, please like put it in the chat. Happy to ask it, and we'll answer the questions. So, um, I'm in the wrong file right now. So we're gonna look at insns.def, which is where all of the YARV instructions are defined. And this is another file you got to be like pretty familiar with because, as I said, like YJIT, we're just translating these YARV instructions to machine code. So you got to know what the YARV instructions do. And I have to apologize. I'm using like Maxime. I know you're not a Vim user. I'm sorry.
It's okay. I know you press I to go to insert mode.
Nice. Okay. Yes. You hit I, I'll hit escape. We can do this together. Okay. So I want to show the send instruction. So this instruction is actually no. Let's look at our test code. Like let's make our test code first. So we're gonna do def pack or our pack thing. Pack. Let me make the font bigger. Let's get that font up there so everybody can read. Yeah, nice. We're making the font big to please the viewers, but it makes us suffer. So we are suffering for your enjoyment. Somebody is asking. Max is asking, why do my lines start at 0? Oh boy, they don't start at 0. I use relative line numbering. So yeah, I'm sorry, Maxime. I know this is terrible. This is so terrible. So whenever you can't say to me, it's I want you to go to line 1. You got to say I want you to go to line 4 up. Okay. So we'll do def pack pack, and let's just take like 3 variables A, B, and C, and then we'll do like A, B, C dot pack, and then we're gonna pass 3 Fs because we want 3 floating point values. And if I create a new, oh my gosh, this font is too big. I'm sorry. We're gonna have to. I can't even. We're gonna have to make that smaller. So if we do mini Ruby dump equals insns on the test RB file, we can see we've got something wrong here. This is not right. It doesn't have our optimization inside of it. It is because of this, the put chilled string optimization, which we need to fix later. That's fine. We'll fix it here. We just need to do frozen string literal true, and then that's okay. It's okay. Jean, this is Jean's fault, but it's fine. We just need to fix it. Not a big deal. There we go. We got our new array. So our new array send is here. So you can see we've got this instruction is the thing we care about in YJIT. And it's got a parameter of 4, which means we need to deal with 4 stack items. And then also pack, which is our, like, that's the method that we want to run. Okay. Anyhow, back over here in insns.def, like, let's look at how we jump into YJIT. Randall says we should propose frozen string literal to be the default on Ruby. I agree with you. I think that is I concur. Yes. Okay, so on send instructions, you'll see like littered throughout the C code, different places. You'll see this macro here, JIT exec. So this JIT exec is like that's how we get into the JIT compiler. So if we go check out oh my gosh. Apparently I can't use Vim either. So JIT exec is a macro, and this macro is like pretty fun to read. But the main thing is that we call into this function here called JIT compile, and JIT compile will return a function pointer here, and then we call into that function pointer here. So we say like, hey, I need you to go compile this particular instruction sequence, which is the method that we're calling into, and it'll go try to compile that, and it'll return a function pointer to us that we'll execute. And by us, I mean the Ruby VM is gonna jump into that function pointer. So it's up to the JIT to generate machine code that the Ruby VM can jump into. All right, so let's go look at JIT compile for a second. So the reason I want to walk through this is I want to show people what is the program that makes colored arrows. It is called ScreenBrush. So the reason I want to talk about this is I want people to know that we're jumping between C and Rust and where that boundary occurs, so that when you're hacking on YJIT, you know like where it came from and where we have to go back to. So we're going to jump into JIT compile, and JIT compile is here. And this code is basically saying like, hey, is YJIT enabled? Right there, we're going to say yes, it is enabled. This also supports RJIT, which is how we enable things like RJIT and HothJIT and TenderJIT, those really great production-ready JIT compilers that I know everyone's using. That was a joke, Maxime, for you. So when we get into this function, we'll see like if there's no JIT function defined already, then what we're gonna do is just increment this counter, and this counter is just how we decide to generate machine code. If we call this counter enough times, then we're gonna go generate machine code. It's just a heuristic, and you can adjust this heuristic. You can say like, hey, I need you to call methods like 100 times or 1,000 times, or 1 time. But you can adjust, like you can actually tweak this on the command line. Now, once we do that, like we'll do RB-YJIT compile ISEC. This thing is the thing that calls into Rust. Right here is our entry point, RB-YJIT ISEC gen entry point. You can see here by these great comments, it is defined in Rust. So if we jump into this function, you'll see, in fact, yes, this is Rust code. We did it. We're in Rust code. It's great. Then I'm not going to walk through the rest of this because honestly, it's like a lot of code, and we have optimization to do. So maybe we ought to do that. Let's go look at the optimization. So we have to implement new array send, and we have to implement the pack version. And interestingly, we already have an optimization like this. Like if we do .hash, so if we do that, like you'll see we have opt new array send, but with hash. So that's already a thing. So basically for the pack version, we just need to implement the pack version of this. So let's go look at opt new array send. Okay. Let's make sure the file type is C. Okay, so we have here in the virtual machine, this is the instruction in the virtual machine. And what it does is it says like, okay, if we got hash, we'll do this function. If we got min or max, so you can see like we have optimizations for hash, min, max, and then pack right here. So in order to implement this in YJIT, the first thing we need to do is open up our code gen. Maxime, I have another question for you.
Sure.
What is your favorite programming language and why is it Ruby?
I feel like that's a trick question.
Yes, it is a trick question. But yeah, I think your favorite programming language is what, Scheme, right?
Oh boy.
That's my favorite programming language.
Yeah, my PhD advisor was obsessed with Scheme. I think he still is.
I
He
mean,
he thinks it's the best language in the universe.
it's the perfect programming language, right? They did everything right. It's like
Right?
that's it.
It was all invented in the 1970s.
Yeah, I mean, the 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 elders knew, I guess.
And any programming idea that you have, someone already did it in the 1970s
Yeah,
on
in
on
Scheme.
a Lisp machine.
Yes, exactly.
But the tapes have been lost in a fire, and so there's no evidence, but you have to believe me.
uh, Max says you must have convinced him of something since he isn't working on Python now. Ooh.
Yeah, I think he's also got a student who's working on
On Python.
basic
Yeah.
block versioning for Python.
Oh wow, really? That's awesome.
Yeah.
Actually, I was curious. What other how many languages use your technique or uses technique?
I'm not sure. I mean, I know there's been some work on Scheme already,
Oh
and
wow.
uh,
Okay.
and JavaScript as well.
You did the one. You did it in Higgs, right? You've implemented this for JavaScript, right?
Yeah. So during my PhD, I built a JIT for JavaScript ECMAScript 5.
Mm-hmm.
It was I mean, it wasn't production ready to the extent that you know that YJIT is, for example.
Mm-hmm.
But it did implement some techniques that are still pretty advanced.
Nice. That's awesome. Okay. All right. Let's go back to our thing. New array send. So we found new array send in ins.s.def. Let's go look for it in codegen.rs. And we actually implement this instruction already in codegen.rs right here in gen op new array send. So you can see this is what it maps to. If we go find gen op new array send, this is the function. So basically what we do is when we're compiling an instruction sequence, we call them instruction sequences, the bytecode for Ruby, we just iterate through each of the instructions and then figure out call a callback in YJIT for implementing that. So here we're looking at new array send, and you can see here we've it actually already implements min, max, and hash. So all we got to do now is just add a pack, add pack support. So I guess let's just do this. Just if the method is pack, then we'll do op new array pack. Does that seem good enough?
Looks legit.
Yes. All right, and then if we make, it's gonna blow up because Russ is gonna say, hey, well, I don't know this function, but there's a similar one called new array hash. Do you want that one instead? And in fact, we do not want that one. It is the wrong one. So let's find new array hash. I'm just gonna steal from that because I'm lazy. Let's see. Let's keep the same signature, I think, is the right thing to do. New array pack. And I think the optimization for new array for hash is very similar to pack. It's just that so the difference is hash doesn't take a parameter where pack takes one parameter. That's the only difference really, right? Pablo asks, was op new array send added to be used used by the JIT like a kind of primitive? And the answer is I don't know. I guess that's hard to say. I'd say no. It's an optimization for the Ruby VM because for YARV itself, because we don't have to allocate an intermediate array. So it does in fact speed up the Ruby VM, but it's also helpful for us on the YJIT side too. So we could call it a win-win. I don't know. Okay. So gen op new array pack. Let's take a look at what the, like, what does hash do? Num? What is num? Ah, that's the number of parameters, right? So like, let's for a second, let's look at the instructions here. So we see like this instruction new array send takes two parameters. One is the number of stack items, and then the other parameter is the method that we want to call. So in our case for pack, we have 4 stack items. That would be the 3 array values, and then pack is the method that we actually want to do on those. Max B is asking, how much of this trouble can you avoid if you have a Ruby implementation of your standard library and inline through the pack function?
Yeah, I think it's pretty difficult to do. Like you have to do a lot of work to make that work, including like escape analysis. Like in order to avoid allocating the arrays, you have to be able to prove in your compiler that the array is not going to escape after your call and things like that. So,
and we can know, like, one thing that's really nice about this optimization is the compiler can know already that this is an ephemeral, like an array that doesn't live. So we already know it at compile time, so we don't need to do that. The main trick though is like we have to be able to detect monkey patching. So if somebody monkey patches pack on array, then we have to be like, oh no, actually, like, we need to allocate an array and do the normal thing. But we already have a mechanism in place for detecting that type of stuff. So like the JIT doesn't need to care. Let's see. All right, so we're gonna get the number of parameters, which in our case, this should probably be 4 for this code. Then what do we need to do next? Save the PC and SP because we may call hash. Okay. Maybe, I guess we should just do the same thing. I don't know. May call pack. This is probably for monkey patches, I'd guess. Like we may call that method.
I think it's to deal with like exceptions and
oh,
and a Ruby GC.
Okay. Now let's see this. What is this doing? This is saying extern C Ruby VM op new array hash. This is just a forward declaration basically, right?
Yes.
And we have this, like we have a version of this in ins and s.def. So we have rbvm op new array pack. So I think we want to do the same, just steal that here. New array pack, what does it take? Oops. It takes an EC, a number, and stack adder from top. Although this one's a little bit different. It's num -1, right? And then stack adder from top. So we're doing a little bit differently than max and min is doing. So, boy, why do I keep doing that? So let's do this. New array pack, and what is hash doing? So this is, what the heck is going on here?
I think we're computing the address of the value at the top.
Ah, okay. So this is computing the address of the value at the top of the stack, and then we're getting a pointer for that, loading it, I guess. So let's go do that. Let's just, I mean, I feel like we can just copy paste most of this implementation. Let's do that, but this one's different. We got to do -num -1.
Yeah, seems a little bit weird to me that this one takes a -1 and when the others don't, but
I think the -1 is because like we have this extra parameter here, like we're pushing the 3 array elements plus we're pushing 1 for the pack.
I see.
1 for the pack parameter. So I can kind of see that. And then this one, oh boy, this function actually takes 4 parameters. It takes the EC, some number, stack adders from top, and then a 4th one. Let's go look at this function. Which is funny. I think
yeah, top and 0 is going to be that string, I think.
Yeah. That's going to be the top of the stack, so it's got to be the string. Okay. So let's do... It's really funny. Okay. My C tags are not around. Let's get grep this guy. Should have run my C tags. INS and helper. Here we go. Okay, so it's a numt value star and then a value, which is our format. So let's fix this. This is gonna be what? Just a value? Is that right?
I think so. Yeah.
My Rust is rusty. Not good. Okay. All right. New array pack. Let's do this. So we get these values OPND, values pointer, and then we are just generating a C call, right? Actually, let's just copy all this stuff because I think it's basically the same. Okay, there. We're generating a new C call, and it's new array pack, and it's gonna take EC num values pointer, and then how do we get top end 0? It's gonna be SPOPND, right?
I believe so.
So this is just gonna be 0? Yeah? Do we have to LEA that? We do, probably.
No, I don't think so, because I think you're just passing the value.
Oh, okay. So we do values pointer. Yeah. Because we have an array. That's right. We have an array of value. We're dealing with an array of values, and then we pass one value as the format string. So we'll do values pointer and then FMT string. So what this is doing is this is generating a call in machine code. It's saying like, hey, I want you to call out to the C function, calculate the pack string, and then return the pack string to me. And then we're going to push that pack string onto the stack. But when we're dealing with like inside of the JIT itself, we're kind of keeping track of all the things that we push and pop off the Ruby stack as well as their types. And you can see like right here we have this thing, like for example, we're popping from the stack, we're keeping track of those stack values. We pop some number off the stack and then we push something onto the stack and we tell it what type that is, so that the next instruction can be like, oh, or any subsequent instructions can be like, I know what type that is. I won't generate any type checks for it, or maybe I do need to generate type checks for it, just depending on what that type is.
In this case, I think we could probably say it's a C string.
Yes, I think so. C string like that. Oh my gosh, like that. Yeah. Type
Yeah,
C
looks
string.
good.
Is num right? We're popping num value. Yeah, that should be right because we're popping those num values off. Yes, I think that's right.
Yeah, only thing I'm not sure about is
this guy.
Yeah.
Yeah, same. Okay. I mean, we'll try it and see what happens.
Try all the permutations with the -1.
Maybe it needs to be -2. We'll see.
Crashy, no crashy.
Yes. All right, let's try it. Uh-oh. What did I do wrong? Let's see. Expected 1 of colon. Oh, okay. It wants a name, I guess. Else. What is that? Let's just do like, I don't know. FMT value. Let's try that. I wonder why it wants a name if it's just a forward declaration. Oh, it's working. Hold on. We just want to make mini Ruby. I don't want to build all of Ruby. Luke is asking, saying great work on YJIT. When is inlining coming?
Well, I guess the good news is it some of it is already here. So we've already started doing some basic forms of inlining in YJIT. In particular, like we inlined something like up to like about 75%, of C function calls, and we also inline some small Ruby functions. I mean, there's it turns out most method calls that we see in production are like trivial like one-liner methods. So we actually Takashi Kokubun has done the work to like inline Ruby methods that return, for example, like a constant string or a constant integer, or maybe basic things like that. And it already buys us like that already inlines like a significant chunk of Ruby method calls.
I mean, that makes a lot of sense because a lot of people implement a method that's like, I just want to return this particular default value or something like that, and then that happens a lot. So it makes sense to inline that stuff. Let's. How should we get the JIT to call this? Let's do def. Just call it like pack 2.0. Let's do 3.0, 3.32, 3.3 Ruby versions. This ought to be enough to JIT compile if we set the threshold to 1, right?
Yeah, and I guess we can always dump the disasm to.
Yes, let's do it. Let's clear, and then if we do mini Ruby dash dash YJIT dash call, and then dash dash YJIT dash call dash threshold equals 1, right? And then test.rb. Oh, and we need to do dash dash what? YJIT.
There's a dash dump dash disasm that's gonna print all the code that gets compiled.
Dump dash disasm. Is that right? Did I?
Oh yeah, you're missing a J.
Oh,
in a YJIT.
Oops. Yeah, this font is too big. I missed it again. Hey, okay. It's not right. I think our one is wrong. So it says no implicit conversion of false into string. This is actually good. This is good. It means that we know that we're JIT compiling that instruction, but it's bad because we got the parameters wrong. So let's go look. SPOPND. I feel that this should be num minus num. I don't think it should be num minus 1. Like, I think that's wrong. Because num is supposed to show, num is the number of stack items in the stack, right?
Yeah, it depends where you want your pointer to start, like at the base or.
Well, so if we look at, like, if we dump the iSeeks from this, shoot, not here. If we dump the iSeeks, you'll see that like new array send is taking 4 as a parameter, and that's where we want to go. We want the 4th item up from us, right? We want ABC, and then we want the last. We want it to ignore the last one. Luke Gruber is asking, does YJIT do CSE and escape analysis?
At the moment, no.
Okay. So I think what we want. I see. Oh, I'm silly. I am a silly person. This is the number of items we want to pack, not the stack address. So yes, we do want minus num here, and then we want num minus 1 into here. Let's give this a whirl.
Yeah, so I think this is saying it's the format that is not a string.
Oh. You know, also, let's do one thing. Let's run it without the JIT and make sure it actually works. Okay, great. It does. So it doesn't like the format then. Okay. What did we do wrong there? Format string, SP, OPND. Does that need to be minus 1? Did I do that wrong? Eh? It must be minus 1.
Could be.
Hey.
Wow.
Oh my
Amazing.
goodness. Oh my goodness. Okay, so let's walk up. Let's look at the machine code that's generated, and then call
Is
it a
there
day.
um is there a pack format? If you could just like pack 3 bytes, then you could look at the output of pack and make sense if
Yeah,
it's right
yeah.
or
Let's
not.
do it. Yeah, let's do it. That's a good idea. Okay, so we'll do like pack 3 bytes. Let's just do like CCC. What should we do? Like 1, 2, 3 seems good. Let's run it and not dump all the stuff. Oh, we should probably print it. Hey.
That's amazing, Aaron.
Nice, we did it. All right. We have implemented it. We have implemented this in YJIT, and I will commit this and push it up. We've hit our hour, so I think we should wrap up here. Um, okay, I think that was it. Uh, as usual, if anyone has questions, leave them in the comments on the YouTube thing, and I will answer anything you have. Somebody's asking, could it be possible for YJIT to inline an equivalent machine code for RBVM new array pack instead of calling the function, maybe allowing more optimizations?
Right. So I think we've talked about this a little bit before, and basically, I think the answer is yes. Like you in YJIT, you could look at the pack string and you could generate a sequence of machine instructions that does the pack faster than calling the C function. Basically, uh, we haven't done that today. I guess to keep things simple, and because there are like a lot of different possible pack options to that you might want to support. But the answer is yes.
Yeah. Okay, cool. Thank you so much for coming on, Maxime. I really appreciate it. It was a lot of fun to have you here. And thank you so much.
All right. Thank you, Aaron. Bye bye.
All right, I'm gonna go back to the thing, keynotes. So I want to say like, thanks for coming on, Maxime. Really appreciate it. It was a lot of fun to hack on YJIT, especially with the YJIT creator. I am going to be going to RailsConf and RubyKaigi, so if anybody here is going to RailsConf or RubyKaigi, say hello to me. Please come say hi. But that also means like I'm not gonna have much time in May, so our next live stream will be May 31st. I'm gonna have Mateus Richard from Thoughtbot on in May, and we're gonna hack on Ruby. I'm not sure what exactly. I think we're gonna hack on primitive stuff. But anyway, thank you everybody for coming. I hope you have a good weekend, and it was fun to do this. Bye.